Okay, so now we're going to look at one-to-one and inverse functions today. So we need to understand this final algebra before we go into trigonometry. So an example of functions which are graphed, I hope that graphically you would know what you would do to check to see if any of these were functions. Let me zoom in on these so you can see them better. Okay. So the way you would check to see if a function is a graph is by checking with the vertical line test, right? Just draw a line through it vertically. If it touches the function only once, then you're good to go. It is a function then, right? All of these, this is only at any point, if you put a vertical line anywhere on this, it's only crossing that one time, so it's a function. Same with this one. Even though there's asymptotes there, it is actually only touching the function one time. Same here with this one time. Even with one of these, which we're going to look at later in the year, coming up soon, one time. Okay. How about these? These are some examples of non-functions. Here, this sideways parabola does not pass the vertical line test. It's crossing it twice. Same here, this nice looking ellipse, even though it's beautiful, it is still not a function. It crosses each vertical line twice in many of the spots. Same with this here. You have this function that is piecewise. There's this line going up to this point and this point going onwards with a different slope line. Here, at this one part here, this one x value does not pass the vertical line test right here. Okay, if there was an open circle there, that would have been a different story. Okay, but on this way, it does not. Here's some examples of functions that are mappings, different ways that you can represent a function. So notice that every x only produces one y value. So on this one here, so every x has one y, x has one y, x has one y. So you can make different different x's go to the same y, that's okay, all right? But every x has one y. Here, this x has two different values, so that is an example of a non-function. Okay, so each x has a unique y, just one arrow coming off of it. Okay, so a one-to-one function is something that we need to know about. A one-to-one function, a unique y for every x, both ways. Okay, so look at this. Here's an example of it so you can see it. So each x has a unique y and vice versa. There is no duplication going on anywhere. Okay, every x has a unique y and every y has that same unique x going back and forth. Okay, same with this. This is an example of a one-to-one function. So is this, and so is this. What do you think that we could do to test a function graphically to see if it's one-to-one? Not only does it have to be a function and pass the vertical line test everywhere, but it has to cross the horizontal line test as well to see if it's one-to-one. Now, one-to-one is going to be important here in a second. You'll see why. Okay, so here, these two y's do not have a unique x, right? They're sharing an x. So this is not a one-to-one function, and it's not a function either, okay? Okay, same with this one. This y does not have a unique answer. It has two different answers there, okay? So that is not one-to-one. Okay. So here's an example, another example of not one-to-one. Look, each x should have a unique y and vice versa. So here again, you can check to see if a function is one-to-one graphically by passing both the vertical and the horizontal line test. Look at this. Is it passing the horizontal line test here? No, this is a big fail. It's crossing it twice, okay? So here's some points to consider. We are now going to go into the world of inverses right here. So inverses are equations where the roles of x and y are switched. Okay, so for example, what you might be considering are that pairs of points are inverses of each other. Domains and ranges, we're going to be looking at that and how to make the inverse of an equation. Okay, we're looking at all of these things. So let's just take a look at this graph for a minute. So we have two functions on here. We have f of x, which is the square root of x plus 2. So it's a square root function that has been shifted to the left by 2. And we have g of x, which is x squared minus 2, or a quadratic that is shifted down by 2. Okay, so f of x is the function in black here. Let me zoom in so you can see that a little better. So this is f of x, this dark one here, and g of x is the blue one here, the quadratic, right? It is a quadratic shifted down by 2, and this was the square root that is shifted to the left by 2. Okay, so let's just take a look at this. Look at some of these points that are on here. What do you see going on between 0, -2 and -2, 0? Do you see a pattern? How about 7, 3 and 3, 7? Do you see something happening here between these points? Maybe like you can even pick some of these other ones in here if you wanted to that are nice, pretty points, like maybe, what is that? Oh, that's not a nice clean point, is it? It's like 1.5, 0. And then here's 0, 1.5. Do you see something going on? Do you notice that the coordinates are exactly switched, the x's and the y's? There's a problem though. What about this point over here, -3, 7? If everything was switched, you would expect 7, -3 to be here. So that's what this is representing over here. Do you see that on this black one here represented? No, you do not. Now, let me ask you another question. Is the square root function, is this a function? Is it passing the vertical line test? Yes. How about the blue one, the quadratic one? Is that a function? Yes, it is passing the vertical line test. But we do have this conflict here if we're talking about inverses. Some of these, right, you're switching the coordinates, but not everything. So here's the idea. Let me zoom out again so you see that. So we have the conflict, right? We were discussing that. What can we do? We can maybe restrict the domain of one of them so that we can maybe solve this dilemma with some of the coordinates there. So we're all about making inverses now. And inverses has to do with, guess what? Functions and whether or not their domains are correct with each other. If I were to restrict the domain, let me zoom in on this one again here. If I were to restrict the domain of this quadratic one here, look, we chopped this whole left half off here. So restrict it so it's everything from 0 and above. X's, all the positive X's, okay? We got rid of all the negative X's over there. So if we restrict it, now all of a sudden, look at this graph. Look how they relate to each other. All of the coordinates are swapped, right? 0, -2, -2, 0. Everything is, all the coordinates have a switch there. Okay, so I'm going to look at this beyond this. So what did I do? What else is going on here? Look at whether or not this function here is 1 to 1. Okay, look at that square root function. Does it pass both the vertical and the horizontal line test? Yes. How about this restricted domain of the quadratic now? Does that pass the one-to-one test? Is it both vertical and horizontal line test? Does it pass it now? Yes. So that is the whole point behind all of this, is if you want to create inverse functions, if you go look at the original before, look at the original quadratic. Does that pass one-to-one? No, right? Because it fails the horizontal line test, it passes it twice. Okay. So if you want to make inverses of functions, you might have to restrict the domain in order to make each function one-to-one. The square root one was already one-to-one, but the quadratic was not. All right, now we see a nice symmetry going on here as well, because look what else. Look what else is going on. This is the line y equals x, this dotted red line. This is the line y equals x. Functions which are inverses of each other are exactly symmetrical about the line y equals x. All right, so this is a big deal. We're going to expect you to know all of these little points. So here, point 1, the x and the y coordinates are switched on inverses, right? You see that here, 0, -2 becomes -2, 0, etc. Not only that, let's look at the domain and range of each of these. Look at the domain of this square root function here. The domain is every x from -2 forward, right, to infinity. What is the range? 0 to infinity, I guess. All right. What is the domain of this one, the square root, the quadratic that has been restricted here? It is from 0 to infinity, and the range is -2 to infinity. What you will notice is that the domain and range of each of these are exactly opposite. Okay, the domain of one is the range of the other, and the range of one is the domain of the other. So here's the point. Point number 1. Let me write it on my board over here so you can see it. Okay. So here's the points. Number 1, the x and y coordinates this is for inverses. This is what happens when you have an inverse. Okay, the x and y coordinates switch. That means if all the x's and y's are switched, that means the domain and the range switch. Okay, to create an inverse, you must have one-to-one functions. So you might have to restrict domain, maybe. Possibly. Maybe not for sure, but it has to be one-to-one. And the fourth thing is that you have symmetry around the line y equals x. Okay, so you have to know these 4 things. You have to know those 4. 1, 2, 3, 4. Okay, must know. So let's go back to our notes. Now I'm going to go back to my writing pad and I'm going to work these examples with you, okay? So let me go back to that again. I'm going to pick the first one, which is this one. So we're going to take a function, an algebraic function, and we're going to write the inverse of that function. So that's what we're doing right now. We're writing the inverse and then we're going to check it. So here's the first thing. First step is switch the x and y. So I'm going to rewrite this. You always know this. F of x is the same thing as y, right? So I'm going to rewrite that. So we have y is equal to x plus 2. So now we're going to do what we said here. We're going to swap the x and the y. So instead of y, we're going to put an x. Instead of x, we're going to put a y. Now we're going to solve for y. Okay, so that is going to be, what are we going to do? We're going to square both sides there, right? To do that, squared, to get rid of the square root, to undo a square root, it's squaring, right? So you're going to get x squared is equal, so the square root and the square, they cancel each other out, y plus 2. And then we're going to subtract 2 from both sides. Okay, so you're going to get x squared minus 2 equals y. Okay, so now the last step is it's not really y, it's actually f inverse. It's the inverse function, okay, because y is up here in the original, okay? So this is actually f inverse of x equals x squared minus 2. So I want you to notice something here. That's f inverse. Okay, this is not an exponent, by the way. I'm going to write that over here. F inverse of x. This is not, that's not an exponent. Okay, a lot of people confuse that. I'm sorry that mathematicians have used that symbol there, but I guess they're running out of things to do. Okay, that stands for inverse in this case. So look at this. Does this look familiar? The square root function and the quadratic function, those two are inverses of each other. So this is what we do again. We switch the x and y coordinates to solve it algebraically, right? This is an algebra example. Okay, so first you switch the x and y. Once you do that, you solve for the y. And then at the end, you replace the y with f inverse, not f to the negative 1. It's f inverse of x. Now we are going to check this right here. Excuse me. So I'm going to move up a little bit so you can see something. So the way you do this is when you do a composition of functions. So check. That means f of f inverse of x is also equal to f inverse of f of x. The answer you should get is x. X. Okay, so either one, either composition, you can do f of f inverse of x or f inverse of f of x. Okay, so we are going to do that. You want to do the first one here? We can check that one out. F of f inverse of x. That means we're going to take the f inverse and plunk it into f of x. Okay, so f of x was equal to, what was it up there? Square root of x plus 2. So f of f inverse of x, we're going to take, go away, we're going to take that and we're going to stick it into the input of that x right there. Okay, so now you can see how compositions and inverses, they're all right. Everything depends on each other. So that would mean we're going to put that square root of function x. We're going to stick f inverse of x, which is this right up here, x squared minus 2. X squared minus 2, that's the f inverse, plus 2, right? Input plus 2. Okay, what does that simplify down to? X squared minus 2 plus 2, so those cancel out, right? Those are gone, and you're left with x squared in there, the square root and the x squared, this, right? The squaring and the square root, they cancel each other out and you're left with x, which is what you're supposed to be left with. Okay, we can do the other way around if you like. We can do f inverse of f of x, just if you don't believe it. So let's try that. F inverse of f of x, which means you're taking this and inputting it into f inverse. So f inverse of x was equal to, what was it again? X squared minus 2. This one right here, right? F inverse of x was x squared minus 2. So you're going to take f of x and stick it in there. F inverse of f of x. You're going to take this and stick it in there. Okay, so that would be the square root of x squared. Sorry, I forgot what f of x was again. Square root of, where is it? Square root of x plus 2. Sorry. Let me erase that away. Square root of, there, erase that. Okay. Square root of x plus 2, right? Input squared minus 2. Get rid of that again now. Sorry. What's that? Okay. Go away. All right. So there's your f of x that we're sticking in there. F of x squared minus 2. Okay, again, here the square and the square root, they cancel each other out. And you're left with x, whatever's inside of that square root that got canceled out, right? X plus 2 minus 2, which equals x. Good. It's all working. That's the way it's supposed to be. All right, let's try another problem. We're going to do exactly the same thing. Let's try this one. This is a pretty easy one. 3x plus 5, we're going to find the inverse. Okay, so we're going to switch the x and the y's. So that's the same thing as y equals 3x plus 5, right? F of x equals y. So now you're just going to switch change there. X equals 3y plus 5. Solve for y. Subtract 5 on both sides. X minus 5 equals 3y. So y equals x minus 5 divided by 3. And that's not really y, it's f inverse of x. There you go. Finished. Boom. Okay. If you need to check it, we can check. Let's just do one of them. Okay. Do it in green. So f of f inverse of x. So f of x would equal 3x plus 5. Is that right? 3x plus 5. So f of f inverse, you do the composition. We're going to stick this into that x right there. Okay. Go away. Sorry, people. So it's going to become 3 times the inputting the f inverse, which is x minus 5 over 3 plus 5, right? We just stuck in f inverse as our input into that. 3 times f inverse plus 5. 3 times f inverse plus 5. Well, guess what? Those 3's cancel out. That's the same as 3 over 1, in case you're wondering. And then you're left with x minus 5 plus 5. Those 2 guys are gone, left with x, which is what you need to be left with after you do the composition. Yes, they are inverses. Let's do one more. And then I should say we are good to go here. So again, this is y. Okay, now you swap your x and your y, so it becomes x equals to y cubed minus 1. Okay, add 1 on both sides. So it becomes x plus 1 equals 2y cubed. Divide by 2 on both sides. Okay, so it's x plus 1 divided by 2 equals y cubed. Guess what? How do you get rid of that y cubed there? You take the cube root of both sides. Okay, so the cube root and the cubing, they cancel each other out. So you're left with y equals the cube root of x plus 1 over 2. And it's not really y, it is f inverse of x. And there you go. So I think I'm going to call this a day here. There's a couple more notes left, which you can check on your own. Okay, so I just worked all of those examples for you. If you want to graph each one of them, here's pictures of the graphs of each one. Here's that cube root one that we just did. I hope you're noticing that there's a beautiful symmetry here between the line y equals x and both of those. Just in case you didn't get that, look at the distance is perfectly equal at any point perpendicular to that line y equals x between the 2 points of each function. Exactly equal on both sides of the graph of each function. Okay. So there's the cube root example. And then here are some example problems of how you would, things you might see on a test or a quiz. So I guess I could talk about that for a second. Verify that both functions f and g are inverses. How would you verify? You would just do a composition of functions, even though they're just called f and g. If you want to know, like that's a good SAT question possibly, right? They just call it two functions f and g, but if you want to know if they're inverses, just do a composition and your answer should be x. So you guys can work this out on your own. The solutions are down below in the notes. How about this? A g of -5 is 3. How would you know what g inverse, that's not an exponent, g inverse of 3 is? Well, and they're telling you g is 1 to 1, so you know that there could be a possible inverse here, right? Well, guess what happens? The x and the y coordinates switch with the inverse. So whatever the y is becomes the x of the inverse, and whatever the x is over here becomes the y. So g inverse of 3 should equal -5. Same with domain and ranges. Domain and ranges swap with inverses, so that's an easy one. So I'm going to skip that last one there in Celsius and Fahrenheit. So here's some of the composition tests and some of the answers to those last couple of problems there. So I thank you very much.